But my name is Andrew Grimes. I'm a senior manager in our Cebu organization. I'm also a NetApp principal technologist. Today was a really proud day for us. We got to announce the MAX Data product formally on stage. So it's live and available, and we can talk about it. So I've also have one of the founders in the room, Sharon. So we may have some questions later on. But feel free to ask questions later on, and I'll go ahead and go through some of this material. But this is a really exciting thing to do for NetApp. We are launching a new product. This was an acquisition of a few years ago of FlexiStore. And we've worked on the product, integrated it with some of our other layers, and now that we're actually releasing it and announcing it today on stage. So again, as always, I'll talk about some futures here. One of the fun things about NetApp, as you're at our Insight conference, we do show you things that are leading or forward-looking. I'm not going to show you confidential material here, but we are going to talk about what the technology is capable of. Not necessarily everything will be released at this moment. So definitely talk to us about what's coming right now, and I'll notate that. But there are some things like server and cloud integration that are also being worked on for future releases. Key thing is this is software, and it is actually innovating incredibly fast. We're not on the typical hardware on-tap release cycles. We're actually able to deliver much, much faster. We're currently thinking of things like a three-month release cycle. We've demonstrated a couple of other products at this event, NDAS, as well as NKS services, and these are actually to be able to release new functions incredibly fast. So you're going to actually see the pace of innovation from NetApp accelerate. So again, we'll talk a little bit about the technology, do an overview, use cases. We put a flex capacitor up here because we thought this was pretty interesting. And I'll tell you about the journey for my life working on Flash. I worked on NetApp AFF for about the last 4 years as part of our Flash turnaround. And we always intended to go further and to really lead the market and where we're going. Performance, we used to think a millisecond was fast. Then we thought 500 microseconds were fast. Currently, we're shipping A800s with 200 microseconds of latency is typically what we talk about. We can get lower than that, but that sounds incredibly fast based on the frame of reference. But we're starting to bring data and data services almost into microsecond and nanosecond timeframes. So we're really starting to think of almost looking forward in time with data. As always, anything you do with NetApp has to have the data fabric in it, and that's actually a big part of why we acquired FlexiStore, because it fit into our data fabric model. It supports the data center, it supports the on-prem hybrid cloud. Typically, that could be considered our HCI portfolio and then our cloud products. And well, this will be clear as we go through, but that was very important to us. We actually did survey the market and looked at other NVMe startups and other technologies that were all really trapped in their hardware and would never work in cloud and would never work in the hyper-converged space. So MAX Data is actually architected to work in all three of these spheres. So key things we're seeing is performance. You can all remember a few years ago, a millisecond was fast, then 500 microseconds is fast. We're now currently saying arrays are 150 to 200 microseconds. That seems incredibly fast, and who would ever want that? But of course, applications have kept up. We're starting to see post-digital transformation. People want the fastest thing possible. Every microsecond of latency out of the applications. Of course, real-time applications are going to do that, but we're starting to see some of those in deep learning, where we actually train algorithms and put them in the data flows and actually scan data as it comes in. So we're starting to see lower and lower latency. The weirdest conversations I've had lately are customers that are literally calling me up saying, I want the fastest thing you can possibly give me. I need 5,000 IOPS. And I'm like, okay, what's it running to? A SQL database. I'm like, that's not a big deal. I can use my lowest end flash box for that. They said, nope, I need every microsecond of latency you can get me out of that environment. I'm streaming data from cars driving on tires into the environment. So it has to keep up with real time. And that was an A800 with NVMe over Fibre Channel with NVMe backend media. And they would pay extra for that low-level latency. But if you're in a competitive industry where every microsecond counts, think financial services, there's a lot of companies using the same market data to make decisions and to make trades. Every microsecond counts if you're competing with someone else. Okay? But we're seeing every microsecond of latency count in some applications. Ironically, the cloud isn't necessarily known for performance, so we're seeing the same requests from cloud, places where performance isn't up to snuff. So what's the journey we've been on? We've gone from spinning disk to hybrid, flash accelerated hybrid to flash, and now to NVMe and NVMe over fabrics. So we planned a few years ago as we were doing our flash turnaround, we realized that NVMe and NVMe over fabrics were coming, and we made a bet there on NVMe over Fibre Channel. That's turned out to be a pretty good bet. We're first to market with that technology. But the real thing was we thought that was a really good low latency platform to start with. And then right after that would come persistent memory. And persistent memory in terms of 3D crosspoint, NVDIMMs, we're also in a couple of other manufacturers are entering into the market. But these are pretty disruptive changes if the architectures that you're working on aren't capable of tolerating change. So we'll talk about more, but this is persistent memory is the next wave of flash innovation, and we're going to see a lot of vendors struggle to keep up with this. The main questions we're having is a lot of customers are saying, how do I use things like Optane DIMMs when they're available in my architecture? Incidentally, we have our Insight Spotlight session going on for the SSSBU unit. We have Lenovo, Intel, and Cisco on stage for the announcement of MAX Data with live demos. So unfortunately, you're here with me. And unfortunately, I'm here rather than in there watching that briefing. But it was pretty exciting to have Intel, Lenovo, and Cisco want to be on stage with us. Okay? And it'll make sense when we get there. So really, where have we been going? We've been going from spinning disk to flash accelerating spinning disk to flash. Flash is about that 200 microsecond latency. Yes, we can get a little lower, but typically there's network in the way. You're on the PCIe bus. You have a bunch of other things that get in the way. DRAM has always been available. It's really fast, it's really expensive, and it's volatile. We've used things like Fusion I/O cards in the past, which took DRAM and used it to accelerate applications. But because it couldn't do writes and couldn't protect the data, you typically had to carefully architect applications that had very limited use cases. It was also very, very expensive for large data sets, so you tended to have to customize the application to only keep very specific things in DRAM. DRAM's not new. Those Fusion I/O cards were around. A lot of people started using them for things, but they kind of petered out in use cases because they were really difficult to utilize. They were also hideously expensive. We still run into them all the time, but they tend to be more niche use cases. The new thing that has come is layer 1 storage class memories. These are things like 3D XPoint, Optane DIMMs, for example, Optane SSDs. These are new memory technologies that operate somewhat at memory speeds, but with the resiliency of 3D NAND. So we're bridging the technology and creating a technology that goes between them.
Hey, Andrew.
Sure.
How do I read the bandwidth row for layer 1 and layer 0? That says 0 seconds gigabytes per second and 0 seconds gigabytes?
It's gigabits per second, and really what we're seeing there is millions of gigabits per second is, I believe, what that was supposed to be. But again, incredibly high internal memory bus speeds, but I would read that as, thousands of gigabits per second. And then typically memory can potentially do millions, but again, it's going to depend on the architecture. What's funny about memory and even SSDs is you can load firmware on them and radically change their performance characteristics. Okay? But the key thing we're seeing here, and actually I had a conversation this morning with someone that needs extremely high throughput in terms of gigabytes per second, and we can actually help with that use case as well. It's not just an IOP conversation. In fact, it's mainly a latency conversation, but we'll go through that. Okay? But the new technology is storage class memories coming. We actually have these today, but there'll be new ones coming shortly. Optane DIMMs are the ones the industry's been waiting for. So NVDIMMs, of course, 3D NAND, DRAM technology on a memory DIMM with 3D NAND backing it up, so you have persistence. The problem with that, of course, is it still is the full cost of DRAM, so it's limited its use cases.
Well, it's
also,
3 times the cost of DRAM because you have to pay for the flash and it's a low volume product.
Yep, so it's very, very expensive. So we see this available today, and we have these in our labs and we're testing. CPOC, our customer proof of concept labs with Netto has actually been testing it. But again, NVDIMM's available today. Adoption has been fairly slow because it's still expensive. The other thing is you can create a RAM drive on it and make things go really, really fast. But you can't back them up, recover them. There's no data efficiency tools. It's basically just another drive. Optane DIMMs are more exciting for that. Not that I will speak for Intel, but the expectation is Optane DIMMs will be cheaper. They will be higher capacity than NVDIMM. You won't need 2 layers, and they will potentially come in much, much cheaper. I've heard as much as 33% the cost of DRAM. Granted, Intel will set those prices on their own agenda. But the opportunity here is to have very, very large amounts of memory speed persistent storage.
Yeah, okay. and the Optane DCs are up to 512 gig.
Yeah.
And the NVDIMMs are 8 or 16.
Yeah. So these are typically, we have a server in our CPOC lab that has 192 gigs of NVDIMM. I've got over a terabyte of Optane DIMM in our lab.
Pockets in that lab, don't you?
Yeah. What was actually interesting was we were talking to Intel about the Optane DIMMs, and they said, what? Would you like another terabyte? And I'm like, yes, please. So again, we've got some cool things with these technologies, but right now NVDIMM is available, but Optane DIMMs are going to be really exciting when those come out. But the challenge is how do you integrate those into your existing applications and your existing infrastructure? There'll be new server architectures and new CPU architectures required. New CPUs will be required, so they will be new servers. But how do you get a database that already exists to take advantage of it without buying the entire capacity? So again, just fitting it into the ecosystem, and I've alluded to this already, we started with our Flash Vision, which was NVMe for the media. We shipped that with the A800. NVMe over Fabrics, which was this low latency foundation, because we wanted to create a host attachment in that 200 microsecond range. The next piece, of course, was persistent memory, and then link them all together in a continuous picture. We've called this our Flash Vision. We've been talking about this for over a year. We're delivering the last piece of this, which is MAX Data. Stepping through it, part of NetApp is the ability to add these changes as they come. We went from spinning disk to Flash to NVMe Flash can all be added to the existing architectures. So if you have a CDOT system, you just add each new generation as it comes out. This is highly unusual in the market where usually new technologies require forklift upgrades, radical changes, and re-architectures. My favorite thing they usually require is abandoning your backups that exist on your systems as you move between generations of technology. So every new announcement is like, ooh, that's really cool. Oh, when am I going to be able to use it? Whereas what we were able to do is each new thing that comes out, you drop it into the environment, you migrate things around online, and you're often going with all your backups in place. NVMe over Fabrics was added as a firmware upgrade. Storage class memory will be used in our storage controllers at a future date. We're not committing to that in this presentation, but persistent memory is another piece. And we always wanted it to exist in the ecosystem around this. When we looked at other acquisitions other than PlexiStore, we looked at NVMe top-of-rack arrays, and none of them can participate in this type of ecosystem. None of them had backup replication technologies. Many of them were very, very limited or specifically targeted at DRAM-based applications. That wasn't what we thought persistent memory brought to the table. Okay.
Andrew, the NVMe over Fabric is Fiber Channel today, is that true?
So NetApp is actually currently shipping a number of variations. Our EF series is currently shipping NVMe over InfiniBand. And barring a startup that we didn't know about, we were first to market with that. NVMe over Fiber Channel, again, barring everyone else, we were first to market with that. We've just released NVMe over Rocky on our EF platform. That's on a roadmap for ONTAP at some time in the future as well. But we've actually found enterprises eager to embrace NVMe over Fiber Channel, and we've had early POCs and adoption. So that's actually been very exciting for us. We bet on Fiber Channel because we thought 2 years ago Rocky looked really sketchy. And we're finding that that was probably a really good bet. It'd be nice to say we're geniuses. We aren't always, but that actually seems to have been a pretty good one. I've also had a lot of conversations about Rocky versus TCP for the next phase. We think TCP will probably be more in demand, and that's what my customers are telling me, but we'll probably do Rocky anyway. Okay.
The enterprises that want data services in an array will be NVMe over Fiber Channel.
Yeah, if you need it fast, you really need it fast, and you're probably already on Fiber Channel is the way I've seen it. What's interesting is you know, and I find this funny, is 10 years ago, and McData, CNT, I can name a couple more for you, there were a lot of Fiber Channel players.
Yep.
There was pretty much one Ethernet player, and that was Cisco. Now where are we? There's about 2 Fiber Channel players. There's about a bazillion Ethernet players. So every time you try to get a spec through, you have to go through all of those layers, get all those people to agree. That's what we're seeing. So we think Fiber Channel is actually easier, predictable, and organizations are able to deploy it. But we always intended to deploy NVMe over Fiber Channel and then add on top of it with a persistent memory technology. So it's been pretty interesting for us to bring this product to market. So MAX Data, what is it fundamentally? Again, the design goals, and you've probably heard this before as part of the PlexiStore discussions with Sharon. Again, faster application response times. Persistent memory gives us the ability to protect reads and writes on the memory bus. And it's actually been really fun for me in some conversations, and I won't mention who it was, but I had a conversation with a company with really, really fast SSDs that literally like, our SSDs are so fast. I said, great, that's my cold tier. And they're like, what? Wait a minute, what? I'm like, we run so fast, we have to be on the memory bus. I have to be that close to the CPU to guarantee my latency and to make best use of the resource. So we are architected for low latency. We get really good throughput. We can wow you with high IOP numbers, but our goal was low latency for the application. We leverage server-side memory on the memory bus because that's the closest to where the application is going to feel it, and you're going to get the lowest microsecond latency possible. We took a software-only approach. We didn't want to get stuck in the box. We didn't want to get stuck in the hardware. I talked to a Wall Street shop recently, and he was all white box. He was testing a bunch of NVMe startups, and he was railing about how great they were and how he wanted white box and how expensive their cards were. I said, great, we're a software product. You can buy your own servers. You can buy your own flash. You can source it from anywhere you want. We will maintain a support matrix, but we wanted that software-defined model, and we'll talk about why that's relevant later. We want to accelerate both read and write workloads. But we actually feel the opportunity is write workloads because nothing's ever served these in the past effectively from a server architecture. But we do reads and writes in a tiering architecture, not a caching architecture. We'll show you that distinction. And then finally, we wanted it to not have to re-architect the application. So we use a POSIX API and an internal mount point on the server. You don't have to re-architect the application to use it. You can drop the application into the mount point and have it run. So it gives you a minimum amount of alteration for the environment. And yeah, plug and play for the application. And then finally, we wanted the ability, if we're going to do writes, we'd better be able to protect them. I come from a storage background. I've been in storage a long time, and back in a previous life, I worked with another company that had a server architecture, and it was really funny watching server people come in to talk about storage. To them, data is transitory. If you reboot the server, somebody else still has a copy. To storage, it is my data. It will always be my data. You want to lose your job? Lose the data. So storage has always had a very paranoid view of architectures. So that's what we wanted to do with this. I look at a server and I see, good God, that thing's going to die any second. So I need the ability to get the data out of the server, get it into an enterprise caliber architecture. So we want it as reliable as possible in the server, but we also want the ability to get it onto 6 nines of reliability. Okay? So enterprise data protection services are a key part of making this enterprise reliable. Okay? So the usual I/O stack we have to deal with, this is all the things an I/O has to do to go from a SAN to a server and to be served. And this is typically reads and writes through failover drivers, network connections, and this is why we're stuck at about that 140 to 200 microseconds of latency. Yes, there are other things going on, RAID access. What's funny is vendors will try and tell you why I can put an NVMe protocol on the last leg of this and I'm going to make things a lot faster. It's like, well, maybe if you had a problem there, that'll help. But for the most part, there's still a whole lot of other stuff going on. And this was the problem we had, was NVMe really belongs on both sides of this chain. And NVMe here is great, but I'm still going over a network for every single transaction. So we wanted to eliminate that, and when we looked at PlexiStore, that's what we saw, was the ability to create a persistent file system on a persistent memory device on the server, on the memory bus, and then store the data there, even if tiering temporarily. Okay? So we eliminate all of this I/O stack and all of this I/O path. It's been a holy grail of storage for a long time to put your data right next to the compute resources. It's been tried a bunch of different ways, namely mainframe way back in the day. But the reality is persistent memory has really opened up this opportunity with lower cost, higher performance, and lower latency right alongside the CPU on the bus. Okay. Question on this? Does that make sense?
So you mentioned the fact that it was a tier but not a cache. So you're somehow have backing storage for this on real storage, or?
Yep. So I'll show you the architecture right now. So this is a software product. This is a software load that you load our application onto a Linux server. We currently support Red Hat 7.5 and CentOS 7.5, although I think there was some discussion about the CentOS support recently. It is actually running on my laptop in CentOS 5 in a Fusion image. Okay? So it is a completely software product. Software product installs, we have a tier 1 space. That tier 1 space is a persistent memory device on the memory bus. It must be a memory device, okay? Because we are addressing it as memory space. The tier 1 space can be DRAM, NVDIMM, or 3D crosspoint when available. DRAM, of course, is volatile, but we support it so you can test with it, or we can conceivably do architectures with DRAM as it's available today in quantities. But long term, we think 3D crosspoint is when this is going to get really, really exciting. The tier 1 space or primary tier is on the server. The secondary tier has to be a block device, because what we're doing is we're actually when I install the when I install the software, I actually configure a configuration file, and I point to the T1 space and the T2 space. When I run the configuration driver, what I'm actually doing is creating the MaxFS file system across both devices. When I go look at the capacity available on that mount point, it is both devices concatenated. It's not caching, it's tiering. Data will be in one or the other at any given time. When I write data into the mount point through a POSIX API, we also do have a memory API, but for the most part, we see the attractiveness in the POSIX API because an existing application can take advantage of it. Merely by copying it into the mount point, it now can run from this combined space between T2 and T1. Normally, you'll see the T2 space is populated with the application, and the T1 space is used for tiering. If I write data into the mount point, it goes to the T1 space. It will be stored in the application structure, whatever that looks like, but it is actually landing on the memory bus, on the T1 space, and then over time, it will be staged down to tier 2.
You support some sort of RAID across NVDIMMs, or?
Nope.
So the protection there is?
I'll get to that. So that's actually funny because one of the server vendors, the server customer I talked to last week asked us if we would mirror NVDIMMs. And we're like, the DIMM reliability is, what was it, 1 to the negative 17th reliability versus a server?
Yeah. Servers are inherently unreliable.
Yeah. I think servers are horrible. I think those guys are crazy, but I'm from storage, so I have to think they're crazy. That's why I always have to have 2 of them as controllers, at least, if not more. But again, this T1, T2 mount point is actually pretty cool because now I can use an existing application. I can take an Oracle, a MongoDB, I can copy it into the mount point. And writes will always go to the T1 space. Reads will go to the T1 space. If it exists in T1, it'll run it from there. If it's not available in T1, it will go to the T2 device.
And it grabs it from T2?
It'll grab it from
Does it
T2.
stage it to T1 before it satisfies the read?
My understanding is it will satisfy the read and move it to T1. So there is a read after read acceleration, and there is a read after write acceleration, and there's an algorithm to try to identify hot space.
So the read is satisfied from T2, but then it's put in T1 after the read is done.
Yes, correct. So again, what we're seeing here is tiering, not caching. And this is a very important distinction because caching's been tried for years. But we will always accelerate writes. Many times we will accelerate reads, but it's going to depend on the architecture. If you're doing first-time read, ETL type stuff, maybe not. Okay. But if you're doing repetitive reads or read after write, you will very likely see T1 acceleration.
Any predictive algorithms on reads as applications are pulling files back?
So typically what we're using is something similar to a cache hot algorithm. So it's looking for frequent file access, and we'll try to maintain that. But again, there's not as much control over it this time. But what we're seeing is, and that's what's unique, is we're finding this is awesome for write workloads. There are ways to accelerate read workloads using caching algorithms and caching techniques like memcached. Writes have never really been effectively accelerated to this level. But what we want to do is actually accelerate both. Again, we have a memory optimized file system called MaxFS here. It's actually been submitted to the Linux kernel as Zeus, Z-U-F-F-S. So Zeus is actually, we're taking it into the Linux ecosystem. The next question everyone always asks is, when is this going to work on Windows? We don't do Windows because of the file system. Okay? Minimal change to the application because I can just drop the application in the mount point and I can accelerate it, right? I'm running on Linux. I don't do AIX, I don't do HBUX, I don't do Solaris, so please don't ask for that either. But Linux makes a lot of sense. We can accelerate persistent memory deployments. The most important thing I hear is, and there was actually an article last week from a hyperscaler that got a shipment of Optane DIMMs, and the article really was, what are we going to do with these? Well, I can take your Optane DIMM, and I can put a T2 device underneath it, and I can give you a mount point, and you don't know the difference. The application won't know the difference. It'll just go really, really fast. Now, back in my test architecture days, making things suddenly go really, really fast is a great way to find bugs. So I can't promise your application won't hit on its own bottlenecks and problems, but I've certainly removed everything possible from that chain. And then finally, this is a software product. So at first release, we will configure it to an ONTAP backend for an ONTAP LUN, and it will configure to multiple ONTAP backend LUNs. But we can also do server. And in fact, I'm doing that on my laptop right now. I actually have it running on a disk file in Fusion. So I have 4 gigs of RAM to a CentOS image, and then behind it, I actually have about a 25 gig SSD file. Get about 200,000 IOPS at it.
Andy, is there any reliance on the ONTAP box being up and running? I mean, because you say it's tiering, not caching. So if there's a problem with the network, for instance, is it going to have to?
It'll stop serving I/O.
Completely. Okay.
Yeah, it needs access to the LUN. So again, I'll go through 2 more architecture slides, but this is the first piece to make sure everybody understands that we are definitely tiering, not caching. We are a software-only product. We will release the ONTAP integration as this announcement, but the server integration is actually extremely easy to do because there's not a whole lot of hooks, right? In fact, it's already running places, and that's been a problem for us. It's how do we tell people not to do stuff? Because it's not, when we configure it to ONTAP, it does run RESTful APIs to configure the backend to make sure it's exactly right. But if I do it to a local SSD device, all I'm actually configuring to is a /dev/SDA BCD. So it doesn't actually see that deeply into it.
So a lot of tiering storage systems require some amount of time to determine what data is kind of active versus not active, and trying to stage that active data into a higher performing tier versus lower performing tier. Do you guys do any of that, or is it pretty much real time? Or
pretty much real time. Writes will always be accelerated.
Data is read from the secondary storage. Do you promote it to the primary?
We'll promote it to primary after first access, and then after we've analyzed the pattern, hot data will be retained while cold data will be ejected.
So there's some amount of time for you to analyze the pattern of read activity in order to determine what to move up. Then, is that what you're saying?
Now they're promoting on first read.
Everything that's read goes in.
But the algorithms are
Yeah,
concerning promotion.
presumably what we're going to do is writes will always be accelerated, and then we will retain those based on capacity, and then reads will be accelerated, but if they're not accessed again for a period of time based on hot-cold access, we'll eject them. So the idea is your reads will trigger them to come in, but we will use an algorithm to decide what to retain and what to eject.
Ultimately, you need to get smarter about the promotion.
Yeah.
Because there's lots of, I only read it once.
So the natural question, of course, working at NetApp, what's the first question everyone asks is, can't that be NFS behind it? I'm writing to files. NFS usually has multiple servers talking to it. I have a really hard time handling file lock across multiple servers from in-memory. So that's something we're working on as a future release, but it is a much harder problem to solve. Hint, FlexCache. NetApp just released a caching technology in 9.5 that allows me to do read and write locking across locations.
Interesting how that's sort of a reverse to the problem that that large in-memory databases have had from the beginning, right? You couldn't put a massive database in memory because you didn't have that capacity. So you'd have to carve up the data sets to work in different workloads.
Yep.
Now you're putting so much together that and into one sort of workload.
Yeah.
You've simplified the database, but you've got other issues that you're trying to struggle through.
So one of the applications we're looking at is Epic for healthcare.
Epic is superb.
So Epic's extremely write latency sensitive. We're like, no problem, but they look like their IOP numbers are going to go radically higher over in the next release. But we have a customer looking at a potentially Epic database of 256 terabytes. So if I can use Optane DIMM to accelerate that with 6 terabytes of Optane DIMM, I can get a pretty big backend database and still get the benefit.
Andy, is there a max ratio between the size of T1 and T2?
Currently, it's 1 to 25. That's what we're recommending, and in fact, we're enforcing it in the configuration script.
Say that one more time.
There's a ratio of 1 to 25, so 1 gig in T1 should be backed up by 25 gigs of T2. So we're doing a fairly fixed ratio right now, although it's something that's fairly easy for us to change later. We're just doing it for performance balancing reasons right now. What we're finding is people who really, really, really need to go this fast right now are usually talking about small databases that are already going really, really, really fast. But we think pretty quickly we're going to start to see the data warehouses and some other use cases.
You're going to see Spark and other types of databases.
Oh, yeah.
Grow.
Yeah, I'll get to that in the use cases, but that's actually been one of the funnest and strangest things about this is we're seeing a lot of people running MongoDB. MongoDB's horrible for in-memory performance, as Rodrigo will love to go on about if you'd like to talk to him. But we can accelerate MongoDB incredibly fast, even in AWS. And there's a famous gaming company with a very publicly blog issue with. Exactly. So that's exactly the use case we would think of. You're running MongoDB, you're running in AWS, latency's couple standard deviations. We can help you with that.
Can I add a comment about the database thing?
Sure.
I think that one of the hardest things to control in a database environment is the working set size, right? The game changer for Max Data in this case is that because it's a file system and it's running, part of this file system is running on top of memory, you don't have actually to be too much worried about the working set size because the tiering is taking care of that for you. So that's a real game changer for databases at least. Okay.
And that's kind of the value of this, isn't it? Is that you are looking at giving this super low latency performance without re-architecting at any level. Really.
Exactly.
Right.
And that was a necessary condition for us. When we looked at the NVMe startups, most of them were going to require a lot of compromises. I've met with a lot of Wall Street shops about this, and it was funny because we started looking at the NVMe startups to acquire, and they were all like, this guy's pretty good, that guy's pretty good, that's pretty good, but always for these little niche use cases and 20 people work for him. But God, you guys really need to look at PlexiStore. And so we did, and we went, damn, this is really cool. And we bought PlexiStore for the product. We also bought it to integrate it into ONTAP. And we're looking at how to integrate it into Element OS and potentially Centricity. So this is a great acquisition on every level. And if I can take a moment, I mean, the engineers we're working with are fantastic. And I've worked with a lot of engineering organizations, and that's really cool as well. So, but the key thing here is we're just doing a very, very different approach. As part of bringing a new product to market, which you don't get to do very often at NetApp, not a brand new product that doesn't have a defined market, we get to meet the analysts, and they're talking to us, and they like to give NetApp a little bit of a hard time because of our years in the flash darkness. And so they're kind of a little bit incredulous about some of the things we talk to them about. They love our cloud story, of course, but it's really interesting talking to them, and suddenly it's like, what are you doing? Wait a minute, what are you doing? Okay, we don't know of anybody else doing this. Nobody's taking this approach to this. This is extremely interesting. Oh, by the way, have you talked to a hyperscaler about how they're going to integrate Optane DIMMs into their architecture?
Hey, Andrew, there's a snapshot and mirror block on this architecture. Are you guys doing snapshots with this data?
Hold that question.
You're doing mirror with this data.
Both. So performance, again, performance is sub 10 microseconds. The next two slides will go through that architecture. So performance, we have a sub 10 microseconds of latency for primary write access. So again, this is a single core, single thread access pattern for multi-core, multi-threaded. And it's actually funny, remember a few minutes ago when I talked about 200 microseconds of latency? We're like, wow, now we're talking 6.9 microseconds of latency. Well, if we do a multi-threaded, multi-core architecture, it could be a little higher, could be as much as 40 microseconds. And then you go, oh, only 40. It's down from 200. And it will always be that. It will be incredibly consistent for you on the server bus architecture, regardless of what's going on with your SAN and your network.
Okay. So single node applies a single core, is that what you're saying? Is that how you would interpret that? And you have multiple node max data?
So let me get to the next architecture. So performance here, I have single server. We do have an ability to replicate the T1 of one server to the T1 of another server. And that adds an additional 2 to 3 microseconds of latency based on our testing. Now, I'll show you the architecture on the next slide. I just wanted to handle the performance together. So you could see we're sub 10 microseconds, but we also have the ability to do replication of that data.
That would be the mirroring thing.
That would be a synchronous mirror. And the way the architecture works is we have an ability to do protecting the writes at memory speed. So we have a snapshot. And what a snapshot does is we trigger the snapshot, or max snap, and it tells evacuate everything from the T1 device. So all the T1 unique data drops down into the T2 device, and if it's an ONTAP system, we'll trigger an ONTAP snapshot, an ONTAP snap mirror, an ONTAP snap vault. So my entire enterprise ecosystem of backup is available. Okay? So this is what we needed for anything NetApp would ever touch. Think NVMe startups that can't, and this was very important for us. The second piece was we have a lot of customers that I hate a server. I think a server is just waiting to die in my paranoid storage background. So I need an ability to protect that T1 data by replicating it somewhere else. If I go to the underlying storage system, I pick up all that network latency anyway. So what we do is a MAX data server can actually replicate to another MAX data server. And the way you configure it is the primary talks to the secondary over a dedicated RDMA network. So we're doing memory-to-memory mapping. We're using an RDMA network, of course, that a little sketchy if you did primary storage with it, but it's perfectly good for server-to-server memory mapping. So what we're doing is every write to the T1 of one server is mirrored to the T1 of the second server.
That takes only a couple of microseconds?
2 to 3 microseconds in our testing.
Okay.
Yeah, we recommend 100 gigabit RDMA private network, but you can have up
and
to...
that's Rocky or...
Yeah, RDMA. And so what we're seeing... I'm sorry?
iWarp?
You know,
I don't think we've done iWarp. I think it's been, Rocky. So again, a couple things here. Primary server replicates to a secondary server. It is an active-passive architecture, but every write will be protected, so we're RPO 0. So yeah, we have an RPO 0 architecture, so you will never lose a write, as long as you don't lose 2 servers.
Okay, and it's an active-passive, and the file system's only available on the master, right?
Correct.
Okay.
So, and it is not twofer, it is 8 sources to 1 destination. So I don't have to pay double for everything. I can have 8 sources replicate to 1 destination. Okay. Obviously, the max recovery server has to have enough T1 space to catch all 8 sources.
Okay.
So that
There's
may
a separate ONTAP LUN associated with the secondary tier or secondary.
I believe we do configure the max recovery server with a LUN, but it's kind of irrelevant because at that point, the only thing that server is actually doing is T1 mirroring.
Right, and if the primary fails, there's a relatively complicated...
The expectation is you will copy the data back. You will not run from the secondary. But you will copy back over the 100 gig RDMA. So one of our MongoDB conversations is really interesting. We actually asked a lot of MongoDB people, what are your 2 biggest issues? And what they've told us that's fascinating is number 1 is data protection, and number 2 is performance. Well, if you shard a MongoDB database in this architecture, we will mirror a shard. Right. If you fail, we can copy that data back over the RDMA network. So we're seeing something on the order of 3 minutes per terabyte copy back times. So we can help MongoDB suck less. That's an official marketing term, by the way.
Let's go back to the... Can you go back to your previous slide?
Sure.
You did a lot of build here. So you're looking at the latency here. Now, is that other slide you showed with you had the Linux stack? Are you saying that was 140 to 200 milliseconds, and then this is what you get because you've eliminated all that?
Correct.
I wasn't one of the ones that was in the Plexi store Tech Field Day, so I'm trying to get my brain around this.
Sure. So what's effectively happening here is this connection, this LUN connection,
Yep.
is running at best 140 to 200 microseconds of latency because of all those things we showed you.
Right.
That can actually be iSCSI, Fiber Channel, or NVMe over Fiber Channel.
Got that part.
From the memory, we will run at single-digit microsecond latencies for single-threaded, single-core because of the Linux scheduler. Okay. If we run multiple threads and multiple cores, and actually, if you're doing high-frequency trading, which I'll talk about that in a minute,
Yep, that was actually.
you'll architect single-core, single-threaded because that is the most important thing for each transaction.
Okay.
So we get a little bit higher. There's a little bit of variation. Honestly, it's because we're in user space and mother may I have the resource.
Okay, and now let's go back to your build. You got your mirroring to this other Max Data server. The primary goes down. You said you're not running off that secondary. You're going to be.
We would restore the primary and copy the data back.
Because it only takes.
Couple minutes to copy the data
Right.
back. So
Damn good recovery right there.
yeah, exactly.
Yeah, and since the application's running in it, it's not like a storage node failure. You can't
Right.
just go, and I'll assume that personality and everybody will reconnect
Yeah.
and it'll be fine.
Everybody always
It's-
asks us, does this
it's
work with
kind of-
rack? No,
It's inherently more complicated than that.
Oh,
yeah. Everybody always asks us if it'll work with rack, and it's like it won't work with rack, but I could have an Oracle database mirror to a second instance of an Oracle database, for example. So if the application mirrors it, I can use multiple. If the application handles the failover, but I can't do the traditional storage failover level.
Right, and that, the 100 and some odd microseconds for typical SSD access, and 10 microseconds for DRAM access. Some of it's all the cruft in the middle, and some of it's that it's flash versus DRAM.
Yeah.
So you've been focusing on write activity. The read activity is roughly the same overhead or less or response?
So reads and writes will be the same if it's from the T1 device. We should see very similar performance characteristics. The only variability is if it's in T1 or not. So that's going to be based on a hot-cold algorithm based on last access. So the things that we've been having, like for example, I've been asked to do an architecture. Actually, Sharon, you did the architecture for a GPU rendering farm. So they have the NVIDIA GPUs that are actually receiving data out of the GPU. So we're actually using the write characteristic to help the GPU run faster by receiving the data after the fact. So we're seeing some really interesting architectural options that we can actually use the writes to accelerate upstream processes. In, again, marketing term, constipated applications.
There was a slide earlier today, or it may have been yesterday, that talked about, exact same hardware running MongoDB versus the exact same hardware running Max Data services, MongoDB on top of Max Data. It was like 11x speed up, I think.
So that's actually one of my last slides that I'll include in here. And that's one of the things that I actually summarize as a point. I'm going to show you some breathtaking latencies. You're not going to see that because performance is always about the black voodoo art of where is my next bottleneck. So the applications are not going to run that fast, but we are going to eliminate absolutely everything from that I/O path that could interfere with it. So you will see a transaction will run that fast, but the time between the transactions won't give you every bit of benefit. Okay?
I'm really impressed with Ray's ability to just see the slides before you project them.
Okay.
I think Ray has a Max Data layer running.
So yeah, it's installed right back here. So that actually brings up a really good point. One of the things that we see about this is you can conceivably get millions of IOPS out of a server or single-digit microsecond latency, but the back-end storage system isn't necessarily delivering the bulk of that performance. So you can have a smaller, more efficient, or potentially even in a server with ONTAP Select, for example, type of device. So we're starting to see this really interesting for edge use cases for accelerating smart edges for IoT, IIoT, or AI inference model, because I can basically take a small device, put an Optane DIMM in it, and make it go like a bat out of hell. And then if I combine it with an ONTAP Select architecture where I'm replicating copies of data, it's like I'm refreshing an AI inference model once a day to look for security scans, that can get extremely interesting. So that's what's been really fun for me is I'm going and talking to customers and it's like, here, let's invent something new with you. As opposed to a lot of times it's like, here's an RFP, what's your cheapest dollars per gig? That's not an interesting world to be in and that's not the world of storage. And it's, for a lot of fun now, that's not the world of NetApp and hasn't been for a while now. The other piece, of course, is cloud. So with ONTAP, we pick up all the ONTAP cloud integrations, Fabric Pool that you saw demonstrated earlier today, NDAS, and some of the other tools. NPS storage, cloud volume services on tap, you pick up some of these integration points where I can use those as replication points to integrate with the cloud. The big thing we're seeing is archiving data out of these environments, backup, snapshots, all the usual stuff. The other thing is this has actually run in the cloud. So we have actually, and PlexiStore did this at an AMI instance that you could check out, and it was literally a pre-built image with, I think, if I remember correctly, it had MongoDB on it. And you could literally go out to Amazon and you could check it out, and it had MAX Data, or excuse me, PlexiStore running on it. It used an EC2 instance with lots of DRAM. It used an EBS backend block device, and it could accelerate data dramatically. You're still running with the cloud overhead on the back end, so you're picking up some latency variability as well as compute variability. But you can go a hell of a lot faster. And in the example of the gaming company I mentioned earlier, there's a blog about them being 10 milliseconds of latency from a MongoDB environment wreaking havoc amongst all of our children who are ready to strangle us. The reality is we could probably put MAX Data in that environment on AWS and accelerate the application with minimal change. Certainly get it below a millisecond. And
Yeah,
our testing has shown significantly lower than that.
I have a question for you. So you've covered a lot of the sort of protection, but what about security and encryption, those sorts of things?
So that's something we're still working on. I actually presented in DC recently, and a lot of the integrators for cover US public, yeah, that's what they asked for. So as of right now, we don't have encryption in the device, but that's also one of the nice things about using an internal block in the server. We're inheriting the security around the server. If the LUN's encrypted, of course that will be, but the memory device we're not currently encrypting.
So Andrew, as it's a tier, anything like SnapMirror or fabric pooling or any of that stuff is really only associated with the data that's on the T2 level.
Mm-hmm.
The T1 data would not be mirrored. Is that true, or not be snap mirrored, rather?
So typically, in typical NetApp fashion, I would trigger a snapshot, which would drop all the data to T2, trigger a snapshot on ONTAP that would have all of the data at that moment in time, and then I would snap mirror a full copy. Now,
When you trigger a snapshot, are you flushing the RDXP, or you still have the data sitting in the NVDIMMs?
so my understanding is when we trigger the max snap, we are pushing all the unique data down to T2. I do not believe it needs
So all
to
the
be
data in the DIMMs is unique data, because it's a tier cache, right?
correct.
Right.
So any data that would be in the NVDIMM or 3DXP would be flushed out to ONTAP, and at that point, you effectively emptied the.
So reads would still be accelerated, but I think in that architecture,
How would reads be
writes,
accelerated?
reads would be purged, or would they
If
be
it's a
maintained?
cache, it would be okay, but if
I
it's
can
a tier,
explain
it
quickly
would-
how the snapshot actually works. We're taking two different snapshots, okay? We're taking a snapshot in MAX Data, and we're taking a snapshot in the AFF. The MAX Snap also includes a service called Sync Snap. We are synchronizing the snapshot to create a coherent single snapshot. And this snapshot now can be mirrored, or you can do whatever you want with the snapshot. It doesn't impact in any way the content of the data in the 3D cross point for that purpose. Okay?
It doesn't purge the
We
read.
do push the relevant data that needs to be pushed, right? The unique data, the new data needs to be pushed
Right.
down to the ONTAP. And
But,
that's a
but
process
that,
that's going to
but
take
that
time.
push is a copy, not a move.
It's pushing a copy, exactly.
Yeah, so you kind of the image remains in memory. It's you're almost taking an image of that, dropping that to disk, and then
Correct,
And so that creates a file system consistent.
Again,
Point.
exactly. It's all about creating consistency,
Right.
right?
Yeah, and
Yeah.
the one,
While applications don't have to be rewritten for this,
yeah.
I would really want to rewrite applications to be the way HPC applications checkpoint,
Yeah.
so that you go, okay, every X transactions or every X minutes, make the disk, the file system, an application consistent point, so that I can create a file system consistent.
Yeah, and we have the APIs on the product to do that yourself right now. Eventually, we'll do that with one of our products. Snap Creator, for example,
Right.
Snap Center is one of the ones we're working on.
And if you did Windows, and I don't blame you for not doing Windows,
The database is
CSS
gone.
would make
Oh, I'm
sense.
sorry. You wanted to go fast? Was that a Windows conversation?
Just to
A
clarify,
SQL stun.
you were explaining that we were
Yeah.
talking about two different
Not good.
types of snapshots, right?
Right.
Right?
Two different snapshots are taken.
Yes.
And we are synchronizing them together in order to create a single coherent snapshot.
Got it.
Eventually,
So-
what you're going to get is a single snapshot.
So the snapshot in Max Data triggers a snapshot on the ONTAP once
Got
it's
it. Thanks.
consistent.
I think I missed that.
And then they get merged together.
I think it was Howard's fault. I missed that.
Of course it's my fault.
And
And in a write-intensive or in implementation, that sync is going to take seconds, right?
I think it's usually extremely fast. The NetApp snapshot
So-
is
That can be too.
You're right. So the snap process itself is extremely fast. It's a microsecond, right? I'm just branching the metadata, but I do need to copy the data down to the second tier. That can take long seconds, 10, 15, 20 seconds. It's done behind the scene. It doesn't block, but until it's not completed, you don't have a coherent snapshot available.
off the
And when I'm speccing the performance of the back end, I have to bear that in mind.
Exactly, absolutely.
And right now, it primarily runs on bare metal with Linux. You've said you've tested that with AWS as well. So are there any plans to kind of bring in support for on-prem hypervisors as well?
Yeah, currently bare metal for first release is our simplest vehicle, and if you really, really, really want to go fast like a bat out of hell, you probably do bare metal anyway.
Yeah.
But we've tested in VMware, I've got it running in Fusion. The software doesn't know. It's, do I have an ability to address the memory device as part of the configuration process? So I have to use a Linux VM, and I have to, have a vSphere 6.7 type of derivative so I can map the memory device to it. So we've done some early testing with vSphere 6.7. We have seen a little bit higher latency, so we are picking up some abstraction overhead. We've also tested with KVM. Naturally, everyone's also asking us for containers, so that's a longer term.
If you want your application to go this fast, you don't want containers in between, and you don't care about the extra $2,000 for the server.
So that's kind of the conversation we're having, but the thing that I think we're seeing here right now is we're doing bare metal Linux as the first release, but like our early access customers, we have 3 doing server only. We have requested server only. We have a number doing ONTAP integration. We have a number actually requesting cloud. And this is a new product and it's software, so it's actually very fast for us to, what do you need? What do you want? Because we're defining a new market here and we're working with our customers on what that needs to be and prioritizing it. Bare metal was the first logical for the first release. We do plan to do vSphere very quickly. It's one of our most popular requests. KVM is another popular request, and cloud is a popular request. We're kind of figuring out, based on demand, which of those make the most sense. But for the most part, they're actually qualification less than software. But we do have functions we want to add to the software as well. And we're doing it on a 3-month cadence, not a 6-month with here's a bunch of hardware. You have to have everything locked before you release. So this is a really fast-moving product.
There's a memory API box on this stack. What does that mean? So you can actually reference the data as memory? Is that this file data as memory?
So I've actually never had a lot of questions about the memory API because almost everybody is looking at using existing applications, but we can receive memory API calls. And I don't know if you want to handle that question.
Sure. So what is a memory API? It's actually interesting. Most applications that want to allocate huge amount of memory, and I'm talking about 512 gig or maybe even a terabyte of memory, actually using that through a system call. It's called memory mapping, and it's actually a file system call. It's the file system is the one who implements the memory mapping, and we are supporting that. So an application that wants to allocate, let's say, 15 terabyte of memory space can do it through this system call, and Max Data will fulfill it. Obviously, portion of it is going to be placed in the 3D cross point, and the rest is going to be based on the second tier. You are going to access it as if it was a memory device, right? Plain linear memory space. Some of it is going to perform at memory speed. Some of it, if the page is missing and I'm getting a page fault, it's going to be fetched from the secondary tier. But you are going to be able to allocate huge amount of memory space based on that technology.
So something like HANA, which would use a large memory, could effectively utilize this solution to do write acceleration, for instance? Or?
I would avoid, putting HANA on something like that. HANA managing its own fast memory and slow memory in the case of 3D cross point. But it can be used for applications like Cassandra. Cassandra is a great example for that.
Okay. So are you planning to do fast memory, slow memory too? Because that memory API would make a lot of sense for DRAM cross-point DC.
Right. So we do have an API to provide customers that want actually to modify the application and use those concepts of fast and slow to tell the system, it's called an F-advise, and you can tell the system, I'm going to need this page soon, bringing it back to the fast memory. I don't need those pages anymore. You can evict them down to the secondary tier.
So I've honestly had very few questions for that so far. Most people are really interested in the POSIX API and the ability to do it retroactively. But it has been fascinating for me. We're starting to get into the high-frequency trading conversations. And to somebody who's been around on Flash for the last 4 years and you've been watching it get faster and faster and faster, I had this really, read the Michael Lewis Flash Boys book, okay? Great book, great read. I was asked to go do an executive briefing somewhere. And it's in New Jersey. I went into the data center. They didn't have my name on the list. They had a room-sized man catcher cage, and they put me through hell to get me into that data center. I get in the data center. There's a glass EBC office right over the racks. And I'm standing there, and I'm like, I know this place. I know something about this place. And somebody finally tells me 70% of the equity trades in the world occur in this building. It was the data center for Flash, high frequency Flash trades. And I was like, holy crap, I'm in the house of the gods for Flash. But I didn't belong there because I wasn't fast enough for any of those workloads. So as soon as I saw Max Data, it was like, I belong in that house now. So that was actually really, really cool. And that's what we're seeing, and that's what the conversations we're starting to have. We're answering high-frequency trade RFPs. That wasn't our world before. We're talking to server vendors. They're on stage with us to announce it. Intel, we're relevant to an Intel conversation. We're having OEM alliance conversations that never would have really seen from NetApp. So this is a really exciting technology for us. It's getting us into memory mapping types of conversations. So the big thing is it's relevant to server, standalone server. We've got early access customers asking us for server access. SAN attach, obviously on tap, but we've already tested it with Element OS. It's just deciding the right release vehicle. Ironically, Element isn't the issue in that case. It's actually the server. And I can take an Element OS and put my own server on it as soon as we agree to support it. But I would really like to have my own server, and that's what we're discussing on the HCI platform. But I personally think Max Data completes HCI, because HCI has always had the promise of compute and data being extremely close together. And if you're using a converged architecture, that's exactly what we think Max Data should add to that. So that's one of our high priorities. That's actually part of why I've moved over to the HCI organization, as well as the cloud integration.
Yeah, but it's a very different use case than typical HCI.
Not today.
Yeah.
But we have a lot of customers, SolidFire customers, that are doing high-performance SQL in SolidFire. Consistent performance, high-performance SQL. But again, the cloud, SAN, and server, this is actually why it's so interesting for me, because we get to kind of play in all three worlds. So we talk to our cloud team and we're relevant. We talk to our SAN team and we're relevant. We talk to HCI and we're relevant. But to customers, it's the same thing. I can go talk about accelerating an application. I don't have to talk about infrastructure. So use cases. These have been really, really fun conversations for us because it doesn't exist in the market today. We know what we want it to do. We know what we've made it to do. But it also can do a lot more things than that. So when we interact with customers, we have an ability to talk well beyond what we recommend. But today, what we recommend is real-time trading platforms. This is any application that every microsecond of latency will count. So obviously, real-time trading applications. In-memory databases, as we've mentioned, the Linux flavors, Cassandra, MongoDB are two examples. But we've had KDB discussions with customers. What's been interesting is seeing the artificial intelligence deep learning process that puts out an algorithm at the end to look at data. Really is interesting to then look at an in-memory acceleration technology, because we're taking an analytics application that used to be run a report at the end of the month to we're training an algorithm that can now look at the data as it comes in. So we can move the frame of reference to real time on an application. AI, of course, is a natural use case, but we're also seeing it with a normal database, a Spark, something that's actually streaming data through, but you want the components analyzing the data running incredibly fast and having potentially larger sets of data that you can look at as you scan.
So, you support something like, I'll hesitate to call it pin or bind or something like that, where you can take a portion of the overall space and lock it into NVDIMM?
So we're currently not pinning data, but I think that's where the memory API would come in.
So you're absolutely right. We do have a function. It's called pin, and it's there. You can tell the system to pin a certain file or even a certain range within a file, and the system will not tear it down in case of insufficient space on the primary storage.
Okay.
Interesting. The thing that we've been seeing that's fascinating to me is we get a lot of requests for NAS acceleration. Naturally, being NetApp, we have a lot of NFS environments, EDA, oil and gas, utilities, and they would like the ability to manage very large NFS data sets. And what we've been doing is actually architecting a few of those to cheat a little bit, which is to actually identify the files you want and copy them into the Max Data mount point, and then we could use the pin function to actually make sure they were read accessible. It's extremely interesting if you start to think of combining it with FlexCache, which is the NetApp algorithm to have a single origin NFS volume and propagate it anywhere in the world. And then I can extract key files from that and pin it into for acceleration.
Do you see yourself doing that? I mean, your customers are asking that, or internal to NetApp is asking you to do that?
Everyone.
Everyone.
Because of our NFS footprint, it makes sense. Because we have a lot of customers doing high-performance analytics on NFS. That's why AWS, Azure, and Google are using us for managed services. So we have a very large footprint in it. Ironically, AFF has mostly been block. We've done a lot of SAN workloads and a lot of SAN performance, but there's a lot of metadata problems in NFS environments and file environments. We can certainly do files. I'm just limited to the block device because of the file locking. But one architecture I did for a customer was we just identified an NFS origin volume, mounted it to that server, and then I use a script with a messaging service to identify the files that should be actually promoted into memory. I don't usually write in that architecture. I usually read, but there are things we can do to accelerate. So there's some creative things. Longer term, we're still trying to figure out exactly how we want the T1 to interact with an NFS as a T2. But we've got some interesting tools with FlexCache to do with it, right? We've already got file locking, multi-site, and propagation.
Sure.
Which if we look at some of our competitors in this space, then they don't even know what persistent memory is yet. But NAS-wise, it would be extremely interesting to me to use MAX Data in the cloud with an in-memory cache acceleration off of ONTAP Cloud set as a FlexCache destination to an on-prem workload. So the last slide I had, of course, was the MongoDB one I mentioned earlier. Everyone will show you some really sexy numbers with low latency, and sometimes we'll show you really sexy numbers with 6 million IOPS out of a server. If you actually go look at Neto on our CPOC booth, he shows a demo of this, and he gets a couple million IOPS out of the server. He's got used to have an iSCSI backend. I think he has a fiber channel backend on that environment right now, but it's a $20,000 server with 192 gigs of NVDIMM in it. I mean, $20,000, oh, what idiots paying that much for a server? Well, versus a massive infrastructure to give you a couple million IOPS, that's actually a deal. But the thing here is you're not going to get every IOP. You're not going to get every bit of latency and every IOP out of the application. The application's going to slam right into its own internal bottlenecks and limits. But that being said, typical MongoDB workload, we saw 3.7 times more IOPS. That's a deal that you didn't have to pay an arm and a leg for because you're getting that resource out of the server. We still recommend a flash array behind it.
Direct access NVMe flash, is that the kind of flash we're talking about?
For the back end?
For the Linux XFS?
I believe Rodrigo ran the test.
And not this one, but I know the details. This one was the one that we ran in an EC2 instance, and it was running on NVMe. It was an NVMe device with XFS on top of it.
So actually, I didn't know that. This is actually an AWS use case. So that's 3.7 times more IOPS in an AWS example, potentially more for an on-prem solution. Latency 6 to 8 times less. It's not going to be 10 microseconds of latency. It's going to be a transaction, and then the application's going to have to catch up. But that being said, you can do this in the server, maybe with 2 servers, instead of $1 bazillion worth of back-end infrastructure.
And this is with like a 1 to 25 gigabyte ratio, NVDIMM to back-end storage kind of thing.
Yep. So that's the ratio. As I said on the previous slide, data warehousing gets a little interesting in those models. So that's something we're still actually kind of investigating. Do you want your data warehouse to write data that ridiculously fast, read data that ridiculously fast? You actually might now, because post-digital transformation, people don't want an end-of-month report. They want an end-of-day report. They want to know, where am I doing now? And then they want to know, what am I going to do tomorrow, which is where the whole AI hype cycle comes in. AI is going to solve world hunger. Well, maybe. Some really interesting tools to look at data more aggressively. But ironically, what I see about the AI inference models is a lot of that is actually very attractive to looking at data as it comes in. So I think you're going to start to see that real time get moved. You're going to see the time horizon move farther and farther and farther into now and possibly into the future with reading data as it comes in and being predictive about it. So we think this is going to fit into those requirements.
And you're just talking about cost of doing some of this kind of stuff. As I understand it, this is not a big ticket item either, MAX Data. It's not a hugely costly thing for people to deploy.
So we're currently planned on a per server license without a core or RAM modifier. So it is a per server. I'm not going to tell you what the cost was because I actually don't know. But we've talked to people about it, and compared to SAN, it's nothing. Compared to a server, okay, it's a little bit of money, but like I said, servers, you throw them away. You kind of expect them to die. But if I can make a server behave like a full SAN array, that gets really attractive.
And you're talking about use cases as well. I mean, is where you see this at the moment, that the value is going to be for those people who want ultra low latency, but on applications that aren't necessarily easily refactored or don't necessarily support that. And you're simplifying the stack quite a lot, aren't you? Because you're taking away kind of the networking back end, because all of that stuff's been just done real close to the processor.
It can conceivably significantly simplify an architecture. The one thing that people legitimately point out is I'm going to fewer LUNs, fewer connections. We don't support Oracle file system because you're in fact loading it onto our file system, so MaxFS. So, excuse me, you can't use an Oracle file system and rack, you have to use ours. So there might be some application modification if you've got a whole lot of things going on. But if you've got a fairly simple Oracle, NoSQL, MongoDB, Cassandra deployment, we can just copy it in and off you go. But where we see things that are interesting is when people are trying to do a lot of complicated application clustering and things like that. SAP HANA is another one. We have been asked repeatedly if this would be a fit for SAP HANA. SAP HANA qualifies the file system. So that's a conversation we have to have with them. Don't know if we have a time limitation, but again, you will get incredible performance out of this. It's just a given. What everybody, and I automatically know who I'm talking to. Oh my God, you got 6 million IOPS? Storage guy. Oh, I got 6 microseconds of latency? Server guy, app guy. Because most of the application people immediately realize latency is what they live for, not a bunch of IOPS. Most of them don't even know what an IOP is. They just don't know when they don't have them. Well, what's been fun for us is we can go talk to infrastructure teams and be like, okay, you can give them so much, they're not going to know what the hell to do with it. So again, fits into our paradigm. We can add this to an existing environment. This can augment what you're currently doing. Now, to be fair, I can't keep a snapshot from an Oracle and on an ONTAP share. I have to move the database in. So I will have to start a new snapshot. But once I've moved the application, I've got snapshot, SnapMirror, SnapVault. As I come out with bigger and badder AFF systems, I roll those in. As I come out with bigger and badder servers with new loads of firmware for Max Data, we can use those jointly in the ecosystem. Okay? And things like standalone server, eventually we're working on when we would support those. Other storage systems for the back end, they actually mentioned it at the keynote. We have the ability to support EF. We've tested with EF already. We've tested with Element OS. We've had requests for VMAX. Maybe not. But that being said, we're not really restricted here because the logic is in the software. The other thing that's really cool about it is we're moving at the speed of the software for future innovations. Not that we want to overpromise what we'll deliver, but we have a lot of flexibility in what we deliver and when we deliver it. That's actually been really cool just as an overview of what NetApp's doing right now. If you understand our NDAS product that was released, it's an extremely fascinating product. We wanted to do a backup technology. It was going to take forever to develop something to run on-prem. So screw it, let's just go develop everything in the cloud. So we actually built everything in AWS, including Elasticsearch integration for all the file analytics and file catalog. I heard it as an idea a year ago. It's a shipping product. And I went and asked them, hey, when are you going to support HCI? It's like, as soon as your APIs are in the Element code, we can support it. And in fact, in 2 weeks after that, I can add a new function. In 2 weeks after that, I can add a new function. Same thing with NKS. It's a cloud service now. We can innovate in that platform as fast as we want. So that's one of the subtle things people don't realize about NetApp right now. We are now innovating at a software cloud pace. We're no longer tied to the hardware. The hardware is important to us. It has to be good. It has to be reliable. I had a meeting with a customer yesterday about an open source white box type of architecture versus our Element OS. And I'm like, 6 nines of reliability, never lose your data, add, grow, remove without disruption. That's storage. It's the only copy of data. I don't want to lose my job. The server guy who suddenly decides he's making storage infrastructure doesn't have that mentality. So that's one of the things that we're starting to see is I can still get the benefits of Element OS, but I can innovate above the line in the software quite quickly now with the way we're architecting. Okay. So again, cool things we're doing, bringing memory, bringing an existing application into in-memory performance. As Optane DIMMs become available and start shipping from Intel, you'll be able to integrate them into your environments, probably with a server upgrade, of course, because there's a limited number of servers. Currently, Lenovo has a model that we're testing. There's an Intel model that we're testing. We don't know about the other server manufacturers, but we think many of them are going to be behind on Optane DIMMs. So you're going to see that really shake up the server vendors. So let's just say a lot of them suddenly got really cozy with us. Let's just say there was a bit of a jostle for getting on stage with us for the event that we just finished. Software-defined flash, of course.
You didn't let the Dell guy get on stage? I don't understand why.
Afraid not, which is ironic because we do actually support them. That's one of our NVDIMM supported systems.
Hey, Andrew, could I ask you to go back to the benchmark page again? I'm sorry.
Sure.
Yeah. So this is a Yahoo cloud serving benchmark that you were running.
So
And what was the memory size that was it like a couple hundred gig or something like that?
I'm not exactly sure, but I think the cache size for the database was 32 gig, right? 64 gig. 64 gig of memory. By default, MongoDB will, if you don't change the cache size for WireTiger on MongoDB, it will allocate 50% of the memory for its cache.
Right. And so in the case of the MAX Data solution there, you had the persistent memory available under MAX Data, but you didn't have any sort of hardware like that for the original benchmark running Linux. It couldn't use it anyways, even if it was there.
You're right. Yeah, we compare a server, or let's call it a regular server.
You were using ONTAP as a backing store, tier 2 store for that solution.
On this test now,
Yes.
we were using NVMe as the second tier.
So you're using direct access, NVMe flash as T2.
Right. That was right.
It was even faster. Right?
Yeah. I've currently got Optane SSDs with Optane DIMMs in test, and it's pretty fast with Max Data on it for standalone server from what we've seen, but we've also seen the NetApp storage attached.
And the latencies you're showing there are transaction latencies, not I/O latencies?
They are the latency reported by YCSB, by the workload generator. So you're saying the application latency. That's what is reported there.
So that's why you'll see 10 microseconds of latency on the previous, but you won't see 10 microseconds here for each transaction because we're picking up overhead in the application stack. But that being said, there's almost no other way to get this fast. Any other questions?
Scale limits.
I'm sorry?
Where are the scale limits where you start to struggle?
So typically, IOP numbers, so we're running FIO, and I think you were on the call with FAF. You were on the call where we ran it with Netto, and we were getting 6 million IOPS out of an HP server. I forget how many cores it was, 192 gigs. Your IOP limits, you're always going to have applications get in the way for the IOP limits. So I think those are really where we're going to start to see bottlenecks is on CPU and on just the transactional throughput for the IOPS. Latency should be fairly consistent as long as the memory is there. And we should never really be able to overrun the memory from my expectation. So I think the limits are going to become transactional in the application.
And it's kind of interesting, you said 50% read, modify, write. It's not 50% writes. It's 50% of the I/O activity is read following by a write. But there's the other 50% which apparently is read only. Is that how I'd read that? It's not like a read to write ratio, right? It's not.
No, that's that's from the Yahoo.
Well, that reflects the operations that we are asking MongoDB to execute. The reads are basically kind of select, because we don't have a select command in there, but they are kind of select, and the writes are update.
Okay.
So we have some Oracle numbers and some other numbers. We have sessions here. I think you guys can attend sessions. So Rodrigo has a MongoDB session, which may have already been presented. Jeffrey Steiner has an Oracle session that I believe may have already been presented. We also have Mike Peppers has a session that goes a deep dive with demo of the GUI, the interfaces, and everything. If you don't want to go, if you don't make it to his session, you can also go see Netto's demo for the CPOC environment that's in the Pavilion Center. The Spotlight session we just did in there also had live demos, but of course we scheduled these at the same time. So we were in here for this. But yeah, I think the key thing here is this is a great technology to accelerate PMEM adoption because I can use PMEM with existing applications with minimal modification. I can drop a server into the environment, I can move the database onto it, and I can start using it right away, and I still have snapshots and I still have replication. So we think this is going to radically accelerate persistent memory. It was fun, we actually did talk with Intel about it, and we were saying, when we went over this technology with them, they said it was fantastic because we can actually mirror persistent memory, which can make it much more adoptable for these ultra-high performance workloads that are RPO 0. We can also protect all of that data with enterprise services, which again makes it much more easier to consume, much more applicable to a broader working set. But the big thing, of course, is retroactively applying it. But we can do tiering, not caching. So it's a much more effective algorithm. It always accelerates writes, which opens up a much more predictable performance profile. But we are relevant to server SAN in the data center. HCI is one of the things we're working on finding the right platform to deliver that on. We're also relevant to cloud. And the cloud conversations have been really, really interesting for us because cloud isn't known for performance.
Doesn't that ultimately require the cloud provider to have PMEM available in their hosts?
So we can do DRAM today.
That's not persistent.
It's not persistent, but their power is probably a little more reliable than our data center, though not recently according to history. But I think the reality is...
You're not implying that EC2 AMIs are reliable, are you?
No, I think the point is you can use DRAM for certain application use cases. NVDIMM, I believe, is available in some EC2 instances, but Optane DIMMs, all of the hyperscalers are getting shipments for them, and they're trying to decide how to deploy them. But the thing that is gating them is exactly how do I integrate them into the existing application stack without compromising these capabilities. Now, the one caveat, of course, is if I put it in the cloud, it's very hard for me to do the server-to-server replication over a private network. So, we definitely have some work to do there on exactly the right use cases and examples. But one of the other conversations we had was a hyperscaler can actually take one of their hyperscaled servers, put out Optane DIMM model, they get a single mount point, and whatever they're doing, like think of Google BigQuery, a Google BigQuery server could probably integrate Optane with this pretty easily.